Hey everyone, thanks for joining. I am Joe Schoonover from Fluid Numerics. I really appreciate you taking time out of your day to join us for this Lunch and Learn with AMD. Just a few housekeeping items before we get started. At any point during this talk, feel free to introduce yourself or ask questions and engage with the content using the chat feature, which you can find on the right side of your screen. We will have a Q&A at the end of the webinar, but you can submit any questions that you have for me anonymously through the question portal, which you can access by toggling over to the Questions tab below your presentation window. You can also post questions through the chat, and I'll do my best to get to all of those at the end of the presentation. Finally, as many folks have asked this at previous Lunch and Learns we've done, this webinar will be available on demand at the conclusion of today's event. So you will receive a link to the recording. So feel free to share it with your colleagues or anyone else that you think might be interested in what we have to share with you today. With that out of the way, let's go ahead and get started. All right. Sorry, I got to pull my notes up here. So yeah, today we're going to be talking about MPI plus programming, particularly with HIP and OpenMP. A lot of the material we're going to cover it should be relevant both for system administrators as well as developers who are working with MPI plus applications. If you've attended some of these Lunch and Learns before, you may have seen this diagram, and this is kind of, I just wanted to make sure we have sort of a consistent mental model. So as we talk about multi-GPU accelerated systems, we all have somewhat of the same picture going on in our mind. So this is a conceptual diagram on the left-hand side of a simple GPU accelerated system that has one CPU socket with its own memory space. It's a single NUMA domain. And on the right of that diagram is a single GPU, and the two are connected to each other over a PCIe switch. The key thing to just keep in mind is, if you haven't done GPU programming before, is that the CPU and GPU have their own distinct memory spaces. And on the right-hand side of this slide is a figure that shows sort of the inner workings at a little bit of a macro scale of a generic-looking GPU. It's got a command processor for taking instructions to run different kernels and issuing them out to the compute units. And each of the compute units on that GPU has a collection of compute cores that can do arithmetic operations in a SIMT style fashion. There's also registers, local cache, and another level of a workload manager that ends up divvying out work on those GPUs in groups of what are called warps or wave fronts. Now, when we get on multi-GPU systems, this diagram becomes a little bit more complicated, and you'll be seeing the diagrams like this showing up throughout the presentation today. But what we typically have is some array of GPUs. So if we look at just like the left half of this diagram, there are 4 distinct GPUs shown here connected to a single CPU socket or to a single NUMA domain over some type of connection. This could be PCIe, these days PCIe 4 with 16 lanes per connection, or it could be the Infinity fabric like you would find on Citonix, Lumi, or Frontier. And the reason why this becomes a challenging problem is of course you now have multiple GPUs that each have their own memory space to work with. You have multiple NUMA domains on a compute node, and so you start to incur these different levels of cost whenever you want to transmit data from one CPU, from one NUMA domain to another, or if you want to go from one GPU to another. There's a slew of pathways that data can go on, and depending on where the data is coming from, where it's going to, this is going to dictate the maximum achievable bandwidth you can have, the minimum latency you can expect for data to go from point A to point B. In addition, I put this sort of empty-looking bar at the top of this diagram because on some systems, particularly those with the Infinity fabric, there are some more direct pathways from GPU to GPU where you do not have to cross into a CPU's NUMA domain to get data moving around. And we'll talk about a little bit today, sort of in this hardware perspective of how you can go about discovering what those pathways are on your system and what you can expect in terms of peak performance going between any of these, between GPU A and GPU B. And then we'll talk a little bit about how you actually just go about doing some basic programming here. Now, as an example of what this looks like on sort of leadership class computing systems, this is a diagram of a Sotonix GPU node. Sotonix is a supercomputer, an HPE Cray system at Palsy Supercomputing Center. What we have in this diagram are 4 distinct NUMA domains. It's the EPYC 7A53 Trento CPU. There's 4 NUMA domains, and within each NUMA domain, there are 2 what are called chiplets that organize basically 8 compute cores that share an L3 cache together. Each chiplet has a connection to what's called a graphics core die. If you're not familiar with the MI250 and 250X, they're pretty unique in the sense that typically what we used to get, even on the MI100 or even the older NVIDIA GPUs, is you would have one physical card for that server, and on that physical card, it hosted a single GPU. On the MI250 and MI250X GPUs, each physical card hosts 2 graphics core dies, which to the end user just looks like 2 distinct GPUs. At any rate here, each chiplet is connected directly to each of these GPU nodes, these GCDs. And then if you're on the same physical card, there is some direct connection between the 2 GCDs that is low latency and high bandwidth. And then down on the bottom half here, all these gray bars and the black bars are showing connections through what's called the Infinity Fabric to get data between GPUs or even off node to any of the 4 NICs that are available. So I'll walk you through just sort of interpreting this diagram in terms of, like, if you wanted to come up with a back of the envelope calculation for peak bandwidth. The way these are usually presented is each of these gray lines connecting 2 different GPUs or connecting a GCD to a chiplet. It represents one lane of the Infinity Fabric, and one lane of the current Infinity Fabric has a peak theoretical bandwidth of about 50 gigs per second. That's gigabytes per second. So between chiplet 0 and GPU 4 here on the left side, the theoretical peak for like a host to device or device to host copy would be 50 gigs per second. Now, if I were to do communications between the GPU 4 and 5, there are 4 Infinity Fabric lanes between those. The theoretical peak would be around 200 gigs. And if you're having trouble seeing the gradients, it's understandable. But we'll cover some tools so you can draw these sorts of diagrams out for yourself. But if I were to look at this connection from GPU 4 to another GPU, let's say if I start on this dark gray line coming out of GPU 4 on the left side, trace it over, it goes to GPU 2. The middle line coming out of it goes from 4 to 2. So there are 2 Infinity Fabric lanes between 4 and 2. And then there's one Infinity Fabric lane. If I follow this last one over, it goes all the way over to GPU 6. So all of these hops that we've discussed so far, from chiplet 0 to GPU 4, from GPU 4 to 5, 4 to 2, and 4 to 6, they only require what's called a hop. There's a direct link between those physical cards. But I'm sure you could imagine a scenario where you're running an application where maybe an MPI process is not sitting on, if you're trying to communicate from GPU 4, for example, to GPU 3, you would have to do some additional, sort of trajectory to get between those instances. One possibility would be from GPU 4 to 2, 2 to 3. Now, a lot of this sort of pathway figuring out is handled underneath the hood for you by libraries like an MPI implementation, but because a lot of how you do your message passing is a little bit controlled in some way, by how you launch your job, how you're doing your task affinity, it's important to understand sort of the connections that are available and what you should be able to expect in terms of peak performance if you got things laid out just right on one of these nodes. Now, pretty much everything we're going to talk about today is going to be focusing on single node MPI, and we will be barely scratching the surface in terms of just getting started with doing the message passing itself, as well as some very basic tuning that you can do based on the types of ways in which message passing can be done on such a system. Now we've talked a little bit about the hardware they're going to be working on. I do need to make a distinction here between the two types of parallel applications that you typically see on these kinds of systems. I like to think about it in two ways. On the left side here, we have what's called embarrassingly parallel, and on the right side is what we call tightly coupled applications. Now, in the embarrassingly parallel world, you typically run many instances of your application, and you're very likely just switching out what data is actually being processed. The key element of an embarrassingly parallel application is that there is absolutely no communication required between these processes. They are entirely independent of each other, and there's no synchronization that is required between individual processes. On the tightly coupled side, on the other hand, you might have one large problem that you're trying to work on, and you divide that large problem into smaller chunks for individual processes to manage. So you still have a lot of instances of your application running, but the main distinction here is that each of those processes need to regularly synchronize and exchange data, and that's the realm of the message passing interface, or MPI, and that's really what we're going to be focusing on today. I'll point out just a few things that I've just noticed working in this realm for some time now, is that the embarrassingly parallel kind of workflows definitely seem to crop up in the artificial intelligence ML, so both the training and inference style jobs. I see it a lot in bioinformatics as well as radio astronomy. Of course, the tightly coupled applications, anything that involves trying to solve a partial differential equation or anything that involves doing particles or grid-based PDE solvers, so things like computational fluid dynamics, molecular dynamics, astrophysics, is where we end up seeing a lot of the tightly coupled style work. So everything we're going to be talking about again today, single node, multi-GPU, primarily these tightly coupled applications that we launch using MPI. As I mentioned at the beginning, the topics we're going to cover are going to be, I think, applicable to folks who do system administration, as well as folks who write applications that use multi-GPU hardware. In my background, I kind of wear two hats. Part of our work is involved in we have our own in-house codes for doing CFD. I mean, I trained as a physical oceanographer, so we do a lot of stuff in that realm, CFD. So we do multi-GPU MPI tightly coupled style applications, but in other areas of our work, we help folks design and run HPC clusters that use Slurm job scheduler, PBS scheduler, etc. And a lot of that work involves doing package management. And so understanding sort of how to speak both these languages, whether you're in one camp or the other, is actually quite beneficial, especially if you start getting in the realm of performance tuning. It's helpful for developers to understand how to communicate to system administrators what's going on in their code, as well as for system administrators to understand what developers are actually trying to do. So yeah, it's really hard to untangle those two areas. So at the top here, we'll start talking about how to discover your hardware topology using some of the tools that are included with ROCm. This will include not just like system diagnostic tools, but we'll be talking about some standard benchmarks you can run that can help you give you a realistic expectation for upper bounds on bandwidth between two different points of communication on your system. We'll then talk a little bit about sort of the details of installing a GPU-Aware MPI. We'll focus primarily on OpenMPI version 5 and above. There are, of course, if you're on an HPE Cray system, you have GPU-Aware MPI. I think that's at that point, it's just how do you go about using that is sort of the next stage. For those of you who are not on HPE Cray systems and have institutional clusters that you're on site that you want to make sure you've got things set up properly for performance, we'll talk about that. And then we'll go over some OSU benchmarks, which can help exercise MPI, particularly to make sure you're hitting the marks you ought to be hitting for your target hardware. Now the next few sections are definitely for the developers. You're going to want to know, especially if you're trying to build portable applications, which I notice a lot of people are really after portability, because none of us in HPC run on a single system anymore. We have, an allocation maybe at a few different institutions, or we have some even our own compute resources at our home institution. And you need to be able to know how to do a detection of whether or not you have GPU-Aware MPI, either at build time for your application or at runtime, just so you have some options in terms of how you want to implement this in your code. This can be a very complicated problem, and it all really comes down to how you want to do things in your code. So my goal here is just to make you aware of the various options you have. And certainly if you have questions on things that maybe things specific to your application, you definitely drop those in the chat. We'll talk, surprisingly, the easiest part of this talk is on how to pass memory pointers to MPI, particularly memory pointers to memory held on the GPU. This has actually gotten quite easy these days, so there won't be a whole lot to cover, unless, of course, if you're in Fortran, there's some silly things you have to do if you're working with HIP Fort, but we'll talk about that. And then the last section here, we'll just start scratching the surface on the two styles of the way in which the OpenMPI and UCX implementation can do the memory copies, and one's using the system device memory architecture, or using what's called a BLIT kernel to do that memory copy. So we'll talk about that and which one you should choose based on whether you're on an Infinity Fabric or PCI system. Okay, so let's talk about how to discover some of your hardware topology. So remember, this is the diagram we started with at the beginning for a multi-GPU system. Your system may or may not look like this. It may have more CPU sockets, may have maybe just one. It might have less GPUs, might have more GPUs, and some of the connections that are on here may not actually be there on your system. But our goal is to figure out sort of the answers to these questions. How many GPUs do we have? How many NUMA domains? What is the distance between these GPUs? That's going to end up dictating the minimum latency you might have for messages to go from point A to point B. And depending on the type of fabric that's between those two locations, that's going to dictate sort of the maximum bandwidth that you can reach. So we want to know the fabric type, we want to know the distance, and then ultimately at the end, we want to know if I'm going from point A to point B, what's the maximum achievable bandwidth. So let's talk about, there's two ways to discover your hardware topology. So I'm going to be showing you some examples from one of the systems we have on site. It's a super micro system with 4 MI210s on it. Now I will say, before even talking about these tools, of course, if you have user documentation that you can refer, always check that first. But in the event that you don't, or maybe you just want to verify and go through the exercise, these tools are here for you. Right. Anyways, here we're looking at some output from ROCm-SMI. This is a tool that comes with any ROCm installation. If you pass to ROCm-SMI the show topo flag, it will spit out a good deal of information for you. Now, what we're looking at here is the first two blocks of information for one of our systems. It's called Noither. It's got, like I said, the 4 MI210s on there with PCIe 4 architecture. And the way this looks, so we'll look at this first section here. It's called the weight between the two GPUs. This is a qualitative measure for the distance that data must travel to reach one GPU from another one. There's not really a physical meaning for the actual values here, But what you can expect is that the higher that value is, the more hops are needed to go from point A to point B. Of course, you can see the correlation between the weights and the hops in these two sections here. So if I were to look at the first column, so the GPU 0 column, and go down each of the rows, of course, it's not going to show any weight to communicate with itself. If you're doing, communications within the same GPU, you're basically working straight out of the global memory on that system, on that particular GPU. But going from GPU 0 to 1 in this case costs me 40 whatever units those are, and then from GPU 0 to 2 or 3, I've got 72 units, right? And of course, this matrix is going to be symmetric because going from point A to point B on these systems is the same cost as going from B to A. Down below, now the hops does have a little bit more of a physical meaning. If I have the way the hops are counted is if I, for example, on this system, if I'm taking 2 hops to go from GPU 0 to GPU 1, what I might start suspecting is that there is no direct connection between GPU 0 and 1. So I don't have a thing like Infinity Fabric, which would allow those 2 GPUs to talk directly to each other. So what this must mean on this system is that I have to go through a NUMA domain on the CPU side and then cross back over the PCI to get to GPU 1. Now, if I look at the connection between GPU 0 and 2, there are 3 hops I have to do, which would be consistent with the idea that I'm going to go from GPU 0 to NUMA domain 0, for example, from NUMA domain 0 to NUMA domain 1, and then all the way over to GPU 3. Now, the next 2 sections of this show topo will tell you the type of link between them. As I mentioned, Noither is a PCIe 4 system. So this one's showing PCIe. Now, if you're on an Infinity Fabric system, you would see something different. It would be XGMI. And then down below, of course, we have the NUMA nodes listed out. And so it tells you the NUMA affinity for each of your GPUs, which again, kind of firms up the story we were talking about in terms of the number of hops to go between different GPUs. So we got GPU 0 and 1 on this system. They're sitting on the same NUMA node. 2 and 3 are on their own NUMA node. So of course, crossing from one NUMA node to the other is what's really going to incur those extra costs for us. So these are things just to keep in mind. Of course, if you're going to fully subscribe a node like this, there's going to be no avoiding having to cross over from NUMA node 0 to 1 to get between GPU 0 and 1 to 2 and 3. But ideally, when you go to do your process affinity mapping for MPI, you would like to minimize the amount of communications crossing that NUMA domain. Now, the other thing you can do, aside from just gathering that sort of qualitative information from ROCm SMI, is run the ROCm bandwidth test. Now, this is an optional package. If you are installing things like ROCm Dev or ROCm HIP or sort of individual packages, you will not have ROCm bandwidth test by default. But if from the administrator side, you can install ROCm bandwidth test from your operating system package manager. Or you can, of course, since everything in ROCm is open source, is download the source code and compile it. And ROCm bandwidth test is going to tell you a lot of the same information. It's going to go through and give you the qualitative information, but it's also going to actually execute memcopy sort of exercises between each of the distinct components on your system. So at the top, the output's going to show you what it's going to refer to in terms of list out the number of devices you have, both CPUs and GPUs, and it will give you those numbers there because all the report that it shows is going to show just these device numbers down below, which we'll see in a second. So this system, we've got 2 of these AMD EPYC 7313s and 4 of those AMD Instinct MI210s. This is still the same Noither system, the Supermicro system we have here. The first one is nothing really special. The first set of output is called the inter-device axis. It just gives you a 1 if there's a connection from one device to another. So if I go along this top row, I've got devices 0 through 5. So my 2 CPUs are 0 and 1. and then the GPUs are 2 through 5. If I go down the columns, I get my device numbers, and if I have a 1 in row 0, column 1, that means there's a connection between device 0 and device 1. So nothing fancy there. You should expect to see that there's connections between all the compute hardware in your system. If you don't, definitely check your installation. Now we have the inter-device NUMA distance. So what I'm going to just have you do mentally is just look at, so remember, devices 2 through 5 were just the MI210 GPUs. This bottom right quadrant of this matrix is the exact same output from ROCm SMI, right? The sort of distance that we had, or the weights between device 2 here and device 3. So GPU 0, GPU 1 was 40, and then crossing that NUMA domain went up to 72. This also gives us is that distance between the CPU and GPU as well. So if I come down, this first column for device 0, in other words, one of our CPUs. If I look at the distance between that CPU and GPU 0, which is device 2, I have 20, whatever these units are. So in other words, if I want to do mem copies between that CPU and that GPU, it's going to cost me 20, whatever. Again, we don't know. I don't have what these units are. There's just qualitative numbers here. But if I want to go between GPU 0 and 1, it costs me 40, which again is consistent with this idea that I'm going from the GPU into the NUMA domain, and then from the NUMA domain back to the other GPU, because I get a cost of 20 to go from CPU to GPU, and then another cost of 20 to go from GPU to CPU, which gives me that 40. Same thing if I want to cross from a GPU in one NUMA domain to the other, I still have that cost of 20 and 20, which gives me 40. But if I want to cross the NUMA domain, it now costs me an additional 32 to get there. Hence why we have the 72 in the GPU to GPU communication cost when you're crossing NUMA domain. So if anything, this just sort of helps fill in the story of what these numbers mean. And then the more interesting thing here is the actual bandwidth tests that are run. This is particularly helpful to do before you even start doing benchmarking with like OSU benchmarks, because it rules out possible issues with like how your BIOS is configured, to make sure like you have simple things set up, like you need to have large bar support in order to get near the peak of PCIe v4. Typically, if you have a super micro system or a gigabyte system, there are AMD on their ROCm doc site has recommended settings for your BIOS to make sure that you're going to get the best possible performance out there. What you should expect for PCIe v4, theoretical peak on those systems is 32 gigs per second one way, so unidirectional. And typically, after you add the operating system layer and other things going on, you maybe will hit about 75% of that theoretical peak sustained, which is pretty reasonable. So what I typically look for when you run things like this on the unidirectional copies, am I above 25 gigs per second in most cases? So of course, if I'm just looking at devices 2 through 5, again, all my GPUs in the lower right quadrant of this matrix, of course, if I go on GPU from 2 to 2, I'm using the I'm basically working straight out of that GPU's global memory. I should get pretty close to the global memory bandwidth, which is about a terabyte per second. So we're doing that just fine. If I go from GPU device 2 to device 3, so these are the two GPUs on the same NUMA domain, I'm hitting 28 gigs per second. And then if I go off NUMA domain, you take a little bit of a hit because you have the extra hop to do. It's also bidirectional numbers that come out of this. So if you do mem copies both ways at the same time, which thankfully for a lot of point-to-point message passing applications, if you do MPI asynchronous operations, you can actually leverage the bidirectional copies quite well. So these are also good numbers to keep in mind. Our bidirectional should be double that 32 gigs per second peak, so 64. And again, when I'm looking at these bandwidth from the bandwidth test, you want to see sustained values that are about 75% of that or above. Which again, that lower right quadrant between, if I look at just between the between GPUs, again, devices 2 through 5, we're doing okay. On the same NUMA domain, we're about 55 gigs per second. We see that on the 2 to 3 and on the 4 to 5 column. And then if I cross NUMA domains, we take a little bit of a hit. Now, all this, I'm painting this picture so we can end up with a simple diagram like this. I've gone through ROCm SMI show topo. I have some understanding of what the topology looks like. I have 2 NUMA domains here. I have GPU 0 and 1 connected to NUMA domain 0. If I were to do copies anywhere on that left half of my system, I would have, for unidirectional copies, or this would be equivalent to our message passing, 28 gigs per second unidirectional, or 55 gigs per second bidirectional. If I stay on the right side, I get the same thing. And then if I want to cross from one NUMA domain to another, I should expect to take a little bit of a hit. This, is a good mental picture to have when you're going into things. So when you want to ask the question of, am I getting enough performance out of my application on the system I'm deploying it on? Having these sort of limits in your mind about what the hardware can actually do is beneficial. So now we have some idea on how to do the sort of hardware discovery. What can happen next is, after you install MPI, of course, if you're doing OpenMPI, there's a lot of different, they call it the modular component architecture. There's a lot of different ways you can do the communication between devices. You can use the built-in lib fabrics. The recommendation from AMD, and what I've found as well in experience, is using the UCX layer, the UCX module for doing communications is it definitely gets you the most performance, gets you closest to these numbers for peak bandwidth that you might see if you were to run the OSU benchmark. So we'll talk about next how to install OpenMPI and what I would say is the right way. Of course, you can install it however you like, and we, I think as we kind of do all this stuff together in the community, I think there's a lot of valuable lessons still to be learned about how to do this stuff. But so far, this is the magic sauce that I think works quite well. I'll give you the basic ingredients here, and of course, later on, I will share a repository where we have some of these scripts available if you wanted just to kick the tires with it. So there's a 3-step process here. If you're doing mostly point-to-point communications, you only need OpenUCX. If you do collective operations, you also need to install OpenUCC. All of these packages use AutoConf as their build system. And during the configure stage, OpenUCX needs to be built with ROCm. So you of course, the assumption here is you have a system with ROCm already installed on it, and you'll basically link ROCm into OpenUCX and the OpenUCC builds. When you build OpenMPI, you'll build OpenMPI not just with ROCm, but also with the UCX and UCC packages that you previously installed. And while there is support for OpenMPI, there is support for AMD GPU-Aware MPI in versions 4. I think it's 4.5. It's not quite complete. So like some of the functions, like for querying whether or not you have GPU-Aware support, they'll return false even if you actually do have that support. So definitely just use version 5 or greater. You can check out the rocm.docs@amd.com for more information on the installation process. We also have, again, as a repository I'll share shortly here, where you can get some scripts. Now, if you want to verify that installation, of course, if you're a user as well, if you ever are using OpenMPI, you want to make sure it has GPU-Aware support for AMD devices. You just run OMPI info. You'll grep for the MPI extensions, and you should see ROCm in that list. Again, AMD GPU support is available in version 4.5, but you will not see ROCm listed in the MPI extensions. Okay, so when you go to do some testing, especially if you're on a multi-GPU system, it's helpful to do device masking so that you can limit which GPUs are participating in MPI point-to-point communications if that's what you're going after for testing. Which, that kind of testing is quite helpful, so you can have some comparison with the ROCm bandwidth test, so you can sort of see the effects of sort of the MPI overhead for doing these communications. But I say you can use either it's ROC-R visible devices, or you can use HIP visible devices, and you can give it a comma-separated list of the device IDs that you want to have available. Of course, if you're using a job scheduler like Slurm, you would need to have the device masking set up in your steatgroups.conf. And then, of course, just let if you let your sbatch command and the sort of flags you send to sbatch rule out which devices you're using. But if you're on a node that does not have that set up, this is underneath the hood, the environment variable that controls that visibility. And then you can do things like run the bandwidth test. Now, if you don't have your MCA configuration set up to have the UCX module used for point-to-point communications, you can just add the --MCA PML for those point-to-point modules, set that to UCX. And then, of course, run the OSU bandwidth test on there. Now, if you are doing the OSU benchmarks, you can add the option -D ROCm. So you're going to do a device ROCm device test, and then the two things you want to communicate between here are device and device. So that's why the DD is there. Again, we have scripts available for this. If you check out github.com/fluidnumerics, there's a repository called GPU programming. Those examples are up there. The top page with the walkthrough, I am actually polishing up. That will be live this afternoon, but you'll be able to find that up online. Again, all those scripts for doing the installation of OpenUCX, OpenUCC, and OpenMPI, as well as OSU benchmarks, are up on that GPU programming repository. Okay, so now for users, we want to know how to detect a GPU-Aware MPI. My preference has always been to do this at runtime, though I have seen a lot of folks use just CPP flags to do that detection at build time and then make decisions at build time. And so you have builds that are sort of specific to the target architecture you're building for. If you want to make one binary that can run on a lot of different systems, this is one way to do it. This example kind of does a mix of both. But in some sense, you kind of have to, especially if you want to run between AMD and NVIDIA GPUs. So I'll walk you through this example here and see. So at the top, of course, you have the include MPI.h. We also need to include the MPI ext header, which gives you this additional function, the MPIX query ROCm support, as well as MPIX query CUDA support. Typically, you might not do this exactly, right? Put both the CPP flags and the query functions in here, because technically both of those are there, and you can call both of them, even if you don't have GPU support. But I did want to just include the CPP flags in there in case you wanted to do just a build time only. But yeah, with OpenMPI, you have the OMPI have MPI ext ROCm. If that guy is defined and is true, then you should expect that you have a ROCm-aware GPU installation. Of course, you can also call this function MPIX query ROCm support. Same thing with CUDA. If you just replace ROCm with CUDA, you can do the same thing. So again, if you want to do it at build time, you literally could just have the CPP flags set, or you just check if they're defined and true. And kind of go from there. But these are the two different ways you could do it. You could do, again, CPP flags, or use the built-in functions to do it. If you're in Fortran, there's no binding for this Fortran function, which is absolutely annoying in my opinion. But I'll show you some ways around this. So one, of course, those CPP flags are there. You can use those CPP flags just as you would on the C side. But if you did want to have that function there, You can use ISOC binding. So Fortran does, do language interoperability, which I've heard some things like, oh, well, coding in C to do Fortran that's not really a solution. And it's like, well, I mean, it is, but that's neither here nor there. So we can use ISOC binding, and this is how you would do it. What you do, of course, you're going to use the ISOC binding module in Fortran, and you'll just make an interface. You'll make a function, you call it whatever you want. My tradition is just to call it the same thing that's exposed in the C library. So here we have mpix query rockem support. We'll bind it to a C function named mpix query rockem support. Now the deal is you do need to write a C wrapper that essentially calls this, because the mpix query rockem support symbol and the object files that come with MPI is not going to be mpix query rockem support. You just need to write a wrapper for this with an extern C function that looks like what we had previously, except we wouldn't call it int main. You would just give it, this function named mpix query rockem support, and go about your business there. But it's really just these few extra lines of code to expose those functions into Fortran. It's not too bad. And again, if you check out that GitHub repository, there's examples up there in the samples subdirectory, in case you wanted to look through those. Now, again, like I said before, Cray MPitch is GPU aware. When you go to compile your application, if you're on Sotonix, Frontier, or Lumi, just make sure you're loading the correct accelerator module before you compile your application. All of those systems I just mentioned have MI250X GPUs, so you're going to load the Cray PE Excel AMD GFX90A module. This makes sure that when you're compiling, the application is built using instructions specific to that GPU. And before you run your application, you need to use MPitch GPU support. You need to set that environment variable to 1. Otherwise, it will not be GPU aware. So unfortunately, like if you want to run on both systems that are Cray and not Cray, or if you even want to use different compilers on the same Cray system, you have different ways in which you can detect if within your source code whether or not there is GPU aware support. So in Cray MPitch, the mpix query rockem or mpix query CUDA support functions are not defined. Instead, what you typically will do is, I mean, I've seen a lot, is just check the environment variable for MPitch GPU support enabled if you're doing this at runtime. Again, the other option is have some kind of build CPP flag that you can detect or that you can set if you really know what you're doing to make sure you're building for a GPU aware system. Now, the cool thing is, I didn't mention it in these slides, is MVAPitch 2 GDR. Actually, they do ship with GPU aware support. There's some extra bits there. I haven't quite gotten around to testing it too deeply yet, but just know that's also another option out there if you're kind of providing these kinds of systems for end users. All right, so let's talk about how to pass memory pointers here. Again, like I said, this is going to be the easiest slide, easiest few slides here. Just a lot of code, so we'll just walk through some of these things here. So at the top here, I'm including a couple things. The most relevant ones are HIP runtime. So we're doing C with HIP here. The next is, of course, we're including the MPI header. Now, in this little main program, this very, very simple program, somewhere along the line, we've allocated memory on the device using HIP malloc. Maybe somewhere in between, we've done some work on this thing, and now we need to send data. So if you have detected that you have GPU aware support, this is just doing a simple send receive pair. So rank 0 is going to send that device buffer from its memory to rank 1, and rank 1 is just going to receive that. It's very straightforward. All you do is you just pass that device pointer. There's nothing fancy going on here. That's literally it. Nothing crazy. So the other routes, if you don't have GPU aware support, right, is you're gonna have to copy from device to host manually using a HIP-mem copy. Do your data exchange, your send receive pair on the host copy of that buffer, and then do a HIP-mem copy back. But hopefully you're on a system where GPU-aware support is available, since there are multiple flavors of MPI where that's possible. Now, if you want to do HIP in Fortran, so you're doing HIP Fort, there's two ways to do this. So the first route is if everything you're doing is using Fortran pointers, and I realize now there's a error here, but this FGPU should be a rank 1 array. But at any rate, so here we're working with two Fortran pointers, which you can do with HIP Fort. HIP Fort, basically, if you're not familiar, it's just an ISOC binding layer on top of HIP. It exposes all of those C functions to you, so you can do your memory management on the GPU from Fortran. And at the top here, what we're doing is just doing a HIP malloc for FGPU. And when we pass that source argument in, what it's going to do is it's going to use the size and shape and type of FCPU to figure out how much space needs to be allocated for FGPU. And then it's going to do a mem copy underneath the hood. So we've updated that GPU copy there. So we have this FGPU. This guy's sitting on GPU memory, and now we want to do send and receive again. So again, rank 0 is going to send to rank 1. Rank 1 is going to send to rank 0. And again, nothing fancy. We just pass FGPU over, no problem. Now, I'll bring up this other scenario because I've seen it done in other applications, particularly those who have done Fortran, even who have carried their applications from the early days of CUDA, and they did CUDA C with Fortran. What we used to do back then, and I still do it, is use type C pointers for that device array. It does make things a little more complicated, unfortunately. So we still here will do HIP malloc on FGPU. When you're using the C pointer, you don't get the nice things like source or mold to detect, what the size and shape and everything of the space you need to allocate for that GPU pointer. So here we just allocate FGPU and how much space. Well, we're going to pull out from size of FCPU. At any rate, so we've got a GPU pointer, FGPU. ISOC binding provides this this function. It's called the subroutine called CF pointer. What that does for us is it will actually return a Fortran pointer for the same C pointer. So it points to the same spot in memory, but it adds the additional things you need for a Fortran pointer. Now that FGPU for MPI is that Fortran pointer. And that is the thing that ends up going through to the MPI send and receive. So if you have things like this in your code where you're using type C pointer for your GPU memory management, you do need to convert from a C pointer to a Fortran pointer and then pass that Fortran pointer through to the MPI send receive pair. So that's really it. But again, it's really not that cumbersome to do this sort of exchange. I think where a lot of the struggle is getting the application running efficiently. Now, the last one I'll point out, and you can do this in C as well, but the example I'll show is in Fortran, is if you're working with OpenMP. And this one's actually quite nice. So here I've got from my data, of course, with OpenMP, you don't have to do the explicit memory management yourself. I've got a real allocatable F. It's got 100 elements here. That's what I got here in the allocate statement. I'm going to allocate 100 elements for that array. We're going to do it's called an unstructured data directive, but we do OMP target enter data, and we allocate F on the GPU. So that one statement there is going to open up a data region, which means anywhere in between this target enter data and a target exit data further down in our code, F will be resident on the GPU. There's going to be a device pointer for that. When you're inside of those kinds of regions, you can use OMP target update to and from to move data from host to device and device to host. When you want to do your MPI send and receive, if you've already got things working in a CPU-only fashion, where you're sending F from rank 0 in this case and receiving into F on rank 1, you can just enclose those if statements, or you can enclose those MPI calls with this directive, OMP target data use device pointer. And at compile time, the compiler will sort out which thing is being sent to the MPI send and receive for you. And of course, if we're using device pointer, it's going to make sure it's doing it directly between GPUs, again, avoiding those superfluous copies between host and device for that exchange. So this is honestly a very elegant solution, and if you're a fan of the directive-based programming, this is quite easy to do. Not a whole lot of work needs to go into it if you don't already have GPU-Aware MPI in your OpenMP accelerated application. Again, all those example codes. So these little simple examples, I've expanded them out quite a bit on that GitHub repository. Again, you can find it on our Fluid Numerics organization on GitHub at the GPU programming repository. The last bit here, it's probably the only thing I can really talk about in terms of performance that I think would have the most applicability to a variety of applications. Because the remainder of a lot of the tuning comes down to making sure that the sizes of your messages that you're sending between GPUs is as large as possible if you want to maximize bandwidth. And then also minimizing communications that are going over long distances, which that's a challenging problem to solve. But if you know your communication patterns and you know your hardware, in theory, you can calculate where you should be placing your processes. But this stuff here, the SDMA versus BLIT kernels, is something that you should definitely experiment with at a first glance, just to try to squeak out an extra bit of performance, especially if you're on the Infinity Fabric systems. Okay, so the default method for memory transfers with both Cray, MPitch, and OpenMPI is through what's called System Direct Memory Access Engines. So the SDMA engines so each MI200 GPU has an SDMA engine, which is distinct from compute units, and their sole purpose is sort of to manage the memory copies between devices. And they're segregated from the compute unit so that you can overlap compute and communication, which can be beneficial. However, the SDMA engines are specifically tuned for PCIe v4 16 lane. And so they're really designed to achieve bandwidth of like 32 gigs per second or 64 gigs per second for the bidirectional. But Infinity Fabric can go much higher than that. If we have 50 gigs per second per connection, between two GCDs on the same card, we know the upper bound is 200 gigs per second. Between some GPUs, it's 100 gigs per second because there's two lanes or two connections of Infinity Fabric. So the point is that the Infinity Fabric hardware does give you a bigger upper bound, but the SDMA engines aren't really designed for that, for the Infinity Fabric. And so the way you can get past sort of the SDMA bandwidth limit is actually to disable SDMA engines. And the OpenMPI implementation, or the implementation of MPI, that either if you're using the UCX or if you're using the Cray MPitch, you can use what's called a BLIT kernel, which it's a compute kernel that will occupy some limited number of compute units on your GPU to actually do the memory copy for you. So it can increase the memory bandwidth that you can obtain. So if you're doing like large packets between GPUs, this is particularly useful if you're able to saturate the Infinity Fabric bandwidth. If you're doing small messages and things like that, it may not be helpful, but it's always worth experimenting because again, there's this trade-off of if I disable SDMA, especially if I'm doing like asynchronous, message passing where I'm doing some compute in the background, I lose the ability to do as much compute during that time. So there's always a little bit of trade-off there. So this is actually a summary of the achieved bandwidth. In blue is showing with SDMA disabled, so that environment variable set to 0. In red, on the left side here, is with SDMA on, and this is on Lumi. And on the right here, I've got just a quick reminder diagram of those connections. This is, again, the same architecture as what you have on Cetonix and Frontier. If I go between two GCDs on the same GPU, which each GPU here is inside of one of these green boxes, I've got 4 Infinity Fabric lanes. So between like 4 and 5, I should have a theoretical peak of 200 gigs per second. And I've got all these various connections between the two. Now, these are showing upper bounds achieved with OSU point-to-point bandwidth measurement. So again, this might not be specific, might not be relevant for your application, but if you're doing large messages, and here I think they were using 16 megabytes packages, so they're getting pretty close to the 200 gig limit. So we're looking at, if I go down the rows here, I'm looking at the various target GPUs, and I'm always looking at a connection between GPU 0. So if I go GPU 0 to 1, there's 4 Infinity Fabric, which would put a theoretical peak of 200. We're hitting about 142. If I have SDMA on, you can see we're capping out at about 50 gigs per second. Just all this really does, again, is highlight the effect of enabling or disabling SDMA. Now, if I look at a PCI system, the story is quite the opposite. So we have two systems at Fluid Numerics here. We have a 4x MI50 system called ORAM. It's PCIe v4. And then we have Noether, which is a 4x MI210, also PCIe v4. The red here is with SDMA on, and blue is with SDMA off. And actually having SDMA on this system is definitely more beneficial if I'm communicating within the same NUMA domain. If I'm going across NUMA domain, it really does not have much of an impact. So it's worth checking this for whatever system you're running on. And of course, your mileage is going to vary depending on how your application is actually doing communication. Like I said previously, the areas where you're going to see most impact is if you are actually saturating the Infinity Fabric bandwidth on your system. So in other words, you're doing large messages, not a whole bunch of small messages. And of course, if you are overlapping compute with your communications, just be mindful of the fact that this can kill a little bit of that asynchronous compute and communication. So in summary, there's GPU-Aware support pretty much everywhere. Multiple MPI flavors provide it. You can do it with OpenMPI. You don't even need UCX or UCC. You can just use the built-in like libfabrics. It's not the best performance. I don't recommend it. I'd say definitely go the route of installing UCX, UCC with OpenMPI and ROCm support. You can do, of course, Cray MPitch comes with it with AMD GPU support, and there's also MVAPitch 2 GDR. In terms of workflow here, I always try to break things down from the perspective of someone who's trying to build an application for a new system that they're getting started on. So always, when you hop on a system, try to understand the compute topology that is there. The tools you have available for that are ROCm SMI to give you qualitative descriptions of CPU and GPU layout. Go through some benchmarking, both with the ROCm bandwidth test as well as the OSU benchmark, so that you can understand sort of the costs of going between various spots in your system. As we saw, GPU pointers are really easily passed between MPI calls with HIP and OpenMP. Nothing really fancy going on there. And then depending on your system and your application, play around with enabling or disabling the SDMA. I think by default on ROCm 5.7 and above, it's enabled. So in those cases, you would just run some tests with it on and run some tests with it off and see how you like it. Okay, so the resources we looked at today, if you definitely recommend checking out the AMD lab notes at gpuopen.com. There's a blog post up there that go through a lot of this material. I definitely lean on those ROCm docs. They've got a lot of good information up there on how to get yourself started, and there's also starting to be some more guidance on performance tuning and things like that. Of course, you can check out our GitHub IO site. We have a lot of documentation on GPU programming as well as coding samples. And if you're interested in finding out more about us, we're not everywhere, but we're in a lot of spots. You can find us on Reddit, GitHub, YouTube, LinkedIn, etc. So with that, feel free to post your questions in the question box or drop them in the chat. I'd be happy to answer those for you. So I did get a couple here. So the first one at the top here is, how should I go about profiling a multi-GPU application on AMD GPUs? So there's a few profilers out there. So you may, if you've already been on AMD GPUs, you probably already heard of like RockProf. Those are that's really good for like single GPU applications, but there's also from AMD Research the OmniTrace, which is helpful for keeping track of both CPU and GPU kernels. You can also see your MPI communications there with OmniTrace. If you're doing single GPU performance, like kernel tuning, things like that, OmniPerf is a good route to go. But I definitely like try to recommend like breaking this problem up to a few, into like a few steps. If you have an application that can be deployed on a single GPU, get single GPU performance down, and look at your MPI communications separately. Which again, OmniTrace is good for that. Not in the AMD realm, but it's relevant. It's from Department of Energy. It's the HPC toolkit. I know a lot of people have, everyone's got an HPC toolkit these days, but Department of Energy's HPC toolkit it's a good profiler that you can use, and you can parse through the profile information in Python with pandas. It's quite nice. I got two more here. What do I do if I'm on a system that does not have GPU-Aware MPI? Well, tell your administrators that don't have a GPU-Aware MPI, and perhaps direct them to the various ways they could set that up, and be nice about it. But within your application, if you're going through like detecting whether or not you have GPU-Aware MPI, the only route is to make sure you copy your device pointers onto the host, and then do your MPI exchanges on the host, and then once you're done with the MPI exchanges, you'll copy those host pointers back to the GPU. The last one here that we have so far. Yeah, if you guys have any questions, again, drop them in the chat or use the questions box at the bottom of your screen. And feel free to ask things about your applications. I'm always interested to hear what you guys are doing. If you have suggestions for things you'd want to see next year at these Lunch and Learns, definitely drop those in the chat. I'd love to hear from you. Okay, so how do we install OpenMPI with support for MPI plus OpenMP for multi-GPU programming? Okay, so like if you have a C application, most of the time there's interoperability. Like if you build the MPI bindings with one C compiler and you use another C compiler to build your application, things are okay. It's Fortran that's particularly problematic. So like if I build my code with one flavor of a Fortran compiler, and MPI is built with a different flavor of Fortran compiler, this can cause problems. And as far as of course, if you're on a Cray environment, you don't need to worry about this. It's all provided for you. But if you're elsewhere, ROCm comes with AMD Flang, AMD Clang, AMD Clang++. When you build OpenMPI, for example, like if you were to go through that, you would want to build OpenMPI using AMD Flang if you're doing Fortran. That will provide you with OpenMP offloading from AMD Flang, and then provide the MPI bindings built with a compatible compiler. And of course, your application would end up being built with AMD Flang. But yeah. We'll give it a couple minutes here. Yeah, if you guys have any questions about MPI programming, I mean any GPU programming at all, I'm happy to answer those for you. Okay. All right. Well, if there's no other questions, thanks everyone for joining and sticking around for this Lunch and Learn. keep an eye out for the next one coming up. We'll see you next time.